Right now, at this very second, something enormous is heading straight for us. Not an asteroid, not a rogue planet, an entire galaxy, 2.5 million light-years away, moving toward us at 150,000 miles per hour. That's not a typo. 150,000 miles every single hour. And here's what makes that number so strange. The universe is supposed to be expanding. Every galaxy should be drifting away from every other galaxy, carried apart by the very fabric of space itself. That's the rule. That's how it works. So why is the Andromeda galaxy breaking it? For years, astronomers scratched their heads at this. Then they looked deeper. Not at the stars, not at the gas, not at anything we can actually see. And they found something hiding in the dark. Something massive. Something shaped like a pancake. And everything changed. Let's start with what we know. The Milky Way and Andromeda are the two largest galaxies in what astronomers call the local group. A loose neighborhood of about 50 galaxies, all bound together by gravity. Most of these galaxies are small, fuzzy, and quiet. But Andromeda is a heavyweight, 1 trillion stars stretched across 220,000 light-years. And it's coming right at us. Now, when scientists first clocked Andromeda's speed, they assumed it was just a random drift. Two galaxies wandering toward each other by chance. No big mystery. Happens all the time in the universe. But the more they looked, the less that explanation held up. The speed was too consistent. The direction was too precise. Something wasn't just pulling Andromeda toward us. Something was guiding it. Like a current beneath still water, invisible but undeniable. To understand what that something is, you have to step back, way back, to a scale so enormous that individual galaxies look like dust. Zoom out far enough, and the universe stops looking like a random scatter of light. It starts looking like a web. Galaxies don't float freely in empty space. They cluster along enormous invisible threads, vast filaments of dark matter that stretch across hundreds of millions of light-years. Where these threads cross, you get the most massive structures in the universe. Galaxy superclusters, cities of thousands of galaxies all pulled together into one gravitational knot. And between these filaments, almost nothing. Giant cosmic voids. Regions of space so empty they make the vacuum of deep space feel crowded. Some of these voids span 300 million light-years across. Our local neighborhood sits at the edge of one. The void is expanding, as all voids do, pushing and stretching the space around it outward. And on the other side of our neighborhood, in the opposite direction, there's a massive filament. A long, flat sheet of dark matter, hundreds of millions of light-years wide and far thinner than it is broad, almost exactly like a pancake. Astronomers now believe this structure, sometimes called a dark matter sheet, is the hidden force reshaping everything in our galactic neighborhood. It's not pulling Andromeda toward us with some beam of targeted gravity. It's doing something more subtle and more powerful. It's compressing the space we both live in. Here's the thing about dark matter that makes it so strange. It doesn't interact with light at all. You can't see it. You can't touch it. You can't detect it with any instrument that relies on electromagnetic radiation, which is basically every telescope ever built. The only way we know it exists is through its gravity. It bends light. It holds galaxies together. It pulls. And it makes up roughly 85% of all the matter in the universe. Most of that dark matter doesn't float around freely. It organizes itself into sheets and filaments, the scaffolding of the cosmic web. And one of those sheets sits right next to us, like a massive invisible wall, curving the gravitational landscape of our entire region of space. researchers modeling the motions of galaxies in our neighborhood found something remarkable. When they included this dark matter sheet in their simulations, suddenly everything made sense. The peculiar velocity of Andromeda, the unusual motion of dozens of smaller galaxies nearby, the way our whole local group seems to be tilting very slowly in one direction. All of it pointed back to the Pancake. The dark matter sheet isn't just influencing the Andromeda galaxy. It's been shaping the destiny of our entire cosmic neighborhood for billions of years, quietly, invisibly, without ever once announcing itself. So what actually happens when Andromeda arrives? The collision is scheduled, and that word is being used loosely, for about 4.5 billion years from now. When most people hear galaxy collision, they picture an apocalyptic smash-up. Stars slamming into stars, fireballs, destruction, the end of everything. The reality is far stranger, and honestly, far more beautiful. Galaxies are almost entirely empty space. The distance between individual stars is so vast that even when two galaxies fully merge, the odds of any two stars actually colliding are astronomically low. Our Sun will almost certainly survive the encounter intact. What will change is everything around us. The night sky, 4 billion years from now, assuming anything is still alive to look at it, will be completely unrecognizable. Andromeda will first appear as a faint smear of light, growing larger over millions of years. Then it will fill the sky. Then the two galaxies will pass through each other, gravitational tides flinging stars into enormous looping arcs, reshaping both galaxies into twisted spirals. They'll separate briefly, then fall back together. Over billions of years, the two great spirals will be sculpted by gravity into a single, massive elliptical galaxy. Astronomers have already given this future galaxy a name, Milkdromeda. The pancake of dark matter that started all of this won't disappear. It will merge with the dark matter halos of both galaxies, becoming part of the vast invisible envelope surrounding Milkdromeda. But here's where the story takes an even more unexpected turn. At the center of the Milky Way sits one of the most studied objects in astronomy, Sagittarius A star, a supermassive black hole, 4 million times the mass of our Sun, compressed into a region smaller than our solar system. At least that's what we thought. A growing body of research is now raising a genuinely radical possibility. What if Sagittarius A star isn't a black hole at all? What if it's a ball of dark matter? The idea sounds outrageous. Black holes are among the most well-established objects in all of astrophysics. We have images of them. We've measured the orbits of stars around Sagittarius A star for decades. The evidence for its existence is overwhelming. But here's the puzzle. The gravitational behavior of objects near the galactic center matches a black hole perfectly in some ways, and doesn't quite fit in others. Some researchers have proposed that an incredibly dense, ultra-compact clump of dark matter could produce nearly identical gravitational effects to a supermassive black hole from our vantage point. The key word is nearly. The differences would be subtle. Tiny deviations in the orbits of stars closest to the center, slight anomalies in the timing of radio emissions, faint imprints in the gravitational waves that next-generation observatories might one day detect. We haven't resolved this yet. The honest answer is, we don't know for certain what sits at the heart of our galaxy. And in science, we don't know is the most exciting sentence there is. What we do know is this: dark matter isn't just out there, far away, in distant filaments and invisible sheets. It may be here, at the very center of the galaxy we call home. Step back once more, way back. Everything we've talked about, the collision, the dark matter pancake, the cosmic voids, the possible dark matter core, at our galaxy's heart. It's all part of the same story. The universe is not a random scattering of matter. It has a hidden architecture, an invisible skeleton of dark matter that has been shaping the large-scale structure of everything since the first hundreds of millions of years after the Big Bang. We are not passive observers of that structure. We are inside it, moving through it, pulled and pushed by forces we can't see and only barely measure. The Andromeda galaxy is racing toward us, not because of some cosmic accident, but because of the deep geometry of dark matter in our corner of the universe. We are passengers on a trajectory set by invisible forces billions of years before Earth even existed. Here is perhaps the most humbling thought to take away from all of this. The most consequential force shaping our cosmic future is one we cannot see, cannot touch, and do not yet fully understand. Dark matter built the scaffolding of the universe. It drew galaxies into clusters. It flattened into sheets. It may lurk at the core of our own galaxy. And 4.5 billion years from now, it will help seal the fate of two great spirals as they become one. The universe has been writing this story for 13 billion years. We're just now learning how to read it.